Hello.
Okay, yeah.
So it's working, the webinar. Okay, and it's my pleasure to present to you this time Simona Bianco. She's coming from Lund University Max 4 Laboratory, and she will speak today about combining mechanics, structure, and dynamics, multiscale analysis of hierarchical functional materials using in situ Rheo-Small angle X-ray scattering. So, Simona, you have 35, 40 minutes. So please, the floor is yours.
Thank you very much. I'm going to start sharing my screen. Hopefully it should work. Um, are you able to see my presentation?
Yes, it's perfect.
It's in presentation mode. Okay, perfect. Okay. So again, thank you, Nico, for the introduction, and thank you for inviting me for the webinar. Today I'll give you a bit of a kind of combination of things that I worked in my PhD, but also what I'm working here now at CoSAXS. So yeah, I'll introduce myself again. I'm Simona. I'm a postdoc here at CoSAXS at the Max 4 Laboratory in Lund University, and also, of course, a junior scientist within the RIANA network, as I represent the LEAPS network. So today we'll discuss about how we can do in situ Rheo-Small angle X-ray scattering experiment to study mechanics, structure, and dynamics all at the same time for functional hierarchical materials. Just gonna quickly, yes, perfect. So this is a brief outline of what the presentation will be about. So I'll introduce the concepts of the hierarchical materials, then SAXS, rheology, and then I'll give you a couple of examples and how we can even further improve Rheo-SAXS by introducing complementary such as PLI and also high temperature and humidity control. So last webinar, people who were there, Devashish made a very nice my field, and this is also where we focus quite a lot at CoSAXS. And so what soft matter is, I really liked the quote from last webinar, things that don't hurt you when you hit it. And essentially, that means quite a lot. So if you can imagine, soft matter encompasses a lot of different materials. So say, for example, we can talk micelles, self-assembling systems, colloids, proteins, liquid crystals, and many, many more. And what makes these materials quite interesting is that there is a very complex interplay between their nanoscale structures, their mesoscale architectures, what happens on the interface, and also how that finally affects the macroscopic properties of the samples. And soft matter is really aimed at understanding this complex interplay and finding ways to study it in a better way. So for majority of the systems, what happens in the terms of their assembly is that they are defined across a lot of different length scales. And this is why we define them as hierarchical materials. The reason why that is that typically for these systems, I've put a couple as an example, they are typically formed on a very small length scale by a single primary particle. These nanoparticles will go over time to cluster, form bundles, and then agglomerates. These agglomerates can then also orient themselves, keep assembling, and become much larger tactoid structures, which will then also have their own orientation and interactions on the mesophase, which means that ultimately they will also influence what happens on a much larger macroscale level in the terms of, for example, fluids, complex liquids, we will have a lot of complex and collective motion being directly dependent on the way that the sample assembles all the way down to the nanoscale. So to study these materials, SAXS and SANS are really useful techniques. You've seen the slide, very similar one from Debashish as well. But basically, we sort of cover the range between 1 nanometer all the way to 300, 400 nanometers. So we can study nanocomposite, nanotubes, nanoparticles, micelles, polymers, etc. But depending on the way that the SAXS is set, then you can also push this limit further to go up to 1 micron. And also, if we have a wide angle X-ray scattering, then we can go down to the more molecular level. So we can cover quite a bit of field, but of course, there's other techniques that can cover the same. So I'm hoping that by the end of this talk, I will convince you that SAXS is a very good technique to study these systems. So in a very typical SAXS experiment, what we do, We have an X-ray source, it goes through a lot of instrument optics, and then the monochromatic beam will hit the sample, which will then scatter at an angle, and we will collect the scattering data on a two-dimensional detector. This basically gives us an information which we call the scattering vector, which gives us the change of the wave vector after interaction with the sample. I've put here, most importantly, that yes, the scattering comes from your sample, but most of the time it's a combination of your sample plus his background. And this will become quite relevant when it comes to data analysis. And also, for most CoSAXS beamlines, we will have variable sample detector distance. So after the X-rays hit the sample, we then have a vacuum vessel, which I've put here as an image with the one that we have at CoSAXS, where we will have a CoSAXS detector. And typically, most CoSAXS beamlines will have it on a trolley so that it'll be movable, going super close to the sample or super further away. This, quite similarly to lenses in a microscopy experiment, will give us different length scales. The closer we go to the sample, the wider angles we get, the more molecular level information we can get. So very small structures. And then if we move really, really far away, we start seeing much larger structures. And in particular, for CoSAXS, we can go up to the 1 micron if we're able to reach, say, distances of like 14, 15 nanometers, which we're able to achieve, for example, at CoSAXS. So what happens when we collect the data? Typically, experimentally, what we do with the two-dimensional CoSAXS data is we do a radial average. So we take a radial integration around all the primary beam, and we put it in a one-dimensional line. This is typically expressed in the measure of scattering intensity, IQ, which is a function of the scattering vector, which is a function of the angle of scattering. We have seen this before from the Bashish talk. It's very similar between SANS and CoSAXS. The principle is exactly the same. So it will depend on a variety of factors. The intensity firstly depends on the difference between the scattering length density of your sample compared to your medium. So this is what I was saying here. Yes, your sample will scatter, but also the solvent in which your sample is will scatter. So you have to make sure that there's a very good difference in the scattering length density between your sample and the background. In the case of X-rays, we care about the difference in electron density. In the case of, for example, neutrons, it will be different scattering length density. The intensity of the scattering will then depend also on the number of the particles, the volume of the particles, and also on the form factor and the structure factor. So the form factor is what we use typically to understand the shape and size of the material. So this is typically coming from the interparticle interference, while the structure factor is typically used to analyze samples that are slightly higher in concentration, as it gives information on interparticle interference. So the spacing between different particles, their interactions, and their phase. For very dilute system, typically the structure factor gets ignored, or we assume it goes close to 1, so it doesn't get included in the analysis. But most typically, if you have a slightly more concentrated samples, you need to start to think about what it means. The important thing about CoSAXS is that CoSAXS is basically scattering as an ensemble average of the whole of the particle in your solution, which means that it will be average of everything that's in your sample. So if you have a mixture of things, CoSAXS will just give you a scattering pattern of everything averaged together. So that's also something to keep in mind. But basically, through analysis, you can get information on the shape, the size of your molecules, the gyration radius, polydispersity, interaction, crystallinity, as well as orientation, which will be very important for today's talk. So why would you want to do CoSAXS compared to other techniques? What's really important for me, especially in the background of soft matter, is that you really need minimal preparation for your samples. We can measure liquids, powders, solutions, and typically most things that your sample will be made in can be fit in a beamline. Of course, you have to consider thickness of your sample because we've said that it depends on the volume and also contrast. So this is something to be thought about, but most of the time you can study your systems in their native state, which is really useful if you think that your sample will change structure, say, after drying. Your samples do not have to be crystalline, and also we can achieve really fast measurements. So you can do in situ studies quite easily. We can go down to the millisecond level, and we can also do time-resolved measurements using lasers, for example. Depending on the sample environment, we can go to really low sample volumes as well. Typically can go down to 20 microliter, for example. Of course, not all things can exist. There's also disadvantages from this technique. And typically, because it's an ensemble average, we have quite low resolution compared to crystallography. And especially for synchrotron radiation, radiation damage is possible for protein systems, for example. So what we tend to do when users come to do SAXS, we want to do radiation damage tests before planning an in situ measurement, because we need to know how much can we expose the sample to the X-rays before creating artifacts. And as I've mentioned before, because the SAXS is an ensemble average, data analysis is a bit hard for more complex systems because you get the average scattering from everything. So typically, SAXS data fitting is also very informed by other complementary techniques, which is why RIANA is also very useful for us, because typically microscopy techniques are used hand in hand with SAXS to make sure that we know what sort of systems we are dealing with. But of course, not all is lost. You still get quite a lot of information from SAXS in terms of the morphologies of your sample. And we tend to divide the SAXS curve in three sorts of spaces. In the very low Q range, we are in the linear region. We get information of the size. We can get information of the radius of gyration. And from the form factor slope, we also get information on the shape of the system. So typically, if there's a slope of -2, then we will have a disk-like particle, -1 will be rod, and 0 should be a spherical particle. And then the oscillations will also give us information on the shape of the system, and we can also gather the size of the system. At really high Q, we then get, according to Pollard's law, information of the surface of the sample, whether the scattering is coming from a smooth surface or a rough surface. So all of this can be done with the analysis, and this can be done in a variety of ways. There's now a lot of softwares where you can just plug in models, say, for example, a model for a cylinder or for a parallelepiped molecule scattering. Or you can do model-free analysis. And it really depends what type of field you're in and what you know about the sample. A lot of this is typically informed by complementary techniques. So what I've mentioned before is that orientation is also quite important, and it can be measured using SAXS. The reason why that is that typically in a normal dilute solution, we will have molecules that are tumbling around. And so their intensity and their orientation of scattering will be radially averaged. So if we were to take a radial integration around the primary beam, we should just see the one-dimensional data. And if we take a very small Q range and integrate it across all angles, we should have a flat line. So the scattering should be all the same. So we call it isotropic scattering. But in most cases, especially when you start looking at samples that are fibrous or if they've been processed in some way, say that they have been 3D printed, then the fibers might have a specific orientation. And the orientation along a direction means that there's also preferential scattering along a direction, which will show in the form of these lobes, typically. And depending on the way that the lobes are facing, then we can also understand which direction the particles are oriented compared to the primary beam. If we do an azimuthal integration, in this particular case, we don't see a flat line anymore, but we see peaks. And from here, we can then quantify the orientation and understand if it's horizontal or vertical. So why are we interested in orientation is that in a lot of industrial processing, most of the sample will be flown. Typically, we will be shearing samples or maybe extruded. So there's a lot of extensional flow. And we can then start studying process systems using SAXS, and so understand how the orientation at a very large scale leads to orientation on a small scale. But how do we quantify macroscopic level orientation? This is how with rheology. So very briefly, rheology is a technique that basically studies deformation and flow of all kinds of material. So rheology covers a significant amount of things, from things that are much more liquid-like, so much more like water, or purely elastic solids. And this is a very nice slide from our collaborators in Chalmers that really show how much rheology encompasses a lot of fields, not only in terms of type of material, but also industrially wise. So I'm a big fan of this gummy bear, so I'll let it be shown to you guys. But for example, slime is a specific example, or food industry uses rheology quite a lot. And as an example, one of the main ways that we use rheology is typically to study the shear viscosity of a sample. In very, very brief words, viscosity is a way to quantify the way that a sample resists to flow. So what we do in a stereotypical viscosity measurement, we have our system on a very static plate, we pour the solution on, and we squeeze it under another rotating plate. The plate then rotates, and we can impart a certain type of shear rate that it will apply on the system, and then we will measure the shear viscosity. So the shear viscosity is a ratio of the shear stress, so the force applied per area, on the shear rate, which is the velocity with respect to the gap between the sample. And these are things that are all controlled, and you can control using a rheometer. And so if you can imagine, if you have a sample squeezed under two plates, you try to move it at a certain speed, the sample may not fully respond immediately. And that retardation is what we sort of quantify to understand what viscosity is. Now, for a purely Newtonian fluid, this is constant. It is independent of shear rate. So say if you can imagine trying to move some water on your hands, it will move exactly the same way as you were trying to brush it off. But other systems will not respond the same way, and they will sort of have different responses. And we can separate them in two very big macro areas. So we have shear thinning samples and shear thickening samples. So shear thinning materials are materials that typically are formed by very long fibers that are entangled together. And as we start to shear them, the fibers will slowly disentangle and then start to orient themselves in the direction of the shear. And so they will oppose less resistance. Shear thickening fluids instead are typically made of samples that might have high concentration of particulates. And so as we try to shear them at really high speeds, then they're going to start to jam together and resist even more the orientation. And as a way to show you, this is a sample from my PhD. So you can see here, this is quite gloopy and viscous, but as I pull them up, the sample starts to flow much faster. So we are shear thinning it even by simply pouring. And this is really important. And so we can use this, and understanding how a sample looks like under these sort of measurements is also very important. So generally, when we do Rheo-SAXS, we have a lot of types of geometries. This is just an example of the three of them that we tend to use, but there's many, many more. So typically, we can offer the concentric cylinders, so a cup and bob, as you can see here. So there's just this big cylinder that goes into a cup, and they have a very, very tiny gap, and we can get up to 20 milliliters of sample, and they're made with polycarbonate. If not, we can use a parallel plate or cone and plate system. These are used for lower volume samples, but also the cone and plate is really important because it has a conical shape with a very, very small angle. But what this does is it applies the same shear rate throughout the whole sample, while in the parallel plate, we have a gradient of shear rates being applied. The main types of tests that we perform typically on the rheometer are steady shear, so we just apply the same shear rotationally on the sample, or oscillatory shear. So oscillatory shear is a way to understand viscoelasticity of the samples. So we apply a very small oscillation on the system, and we see how easily the system will bounce back. So quantify how much energy is being lost and how much is being stored. So to see how much the sample is solid-like or liquid-like. So we have rheology, so we have macroscale information on the sample, and we have SAXS, so we have nanoscale information on the sample. You can imagine this can be really useful. If we put them both at the same time, so to do Rheo-SAXS experiment, we can characterize the sample simultaneously on the bulk level and on a nanoscale level, and really gain information on macroscopic flow behavior and how that is defined by nanoscale structures, if there's any structural changes under deformation, and also if we have macroscale processes, say for example, gelation of a system, polymerization, then we can see what happens on the nanoscale level as the sample progresses, because we can track that progress with the rheometer, but we can also look at it using SAXS. As an example, I wanted to show an example from my PhD. So in the group that I used to work with in the Dave Adams lab at the University of Glasgow, we worked with functionalized dipeptides. So we have these very short dipeptide molecules functionalized at one end with a hydrophobic moiety. The reason why they're built in this way is to give the samples a balance between hydrophobicity and hydrophilicity to be able to self-assemble in water to form micellar structures. So this sample by itself forms very heterogeneous tape-like structures. Now, this is a nice fit to the data, but this we wouldn't know if we didn't do any cryo-EM. So it's important to note that a lot of these fits are driven by complementary techniques because the sample is really heterogeneous. So you could fit a lot of different models to these sample. What we've noticed for the system is that by itself, it looks kind of like water-like. Very low viscosity, very heterogeneous sample. But if we do add any salts to it, we have visual changes immediately. So we get much more turbid solution and very, very big increase in viscosity. In particular, it seems that the change in viscosity is cation dependent rather than anion dependent. And so, of course, to understand what was happening in the system, we turned to CoSAXS. And what we were able to see is that in the case of all three salts, three types of salts, we get three different cases. In most of the cases, we see fiber-like structures, so they're all fitted to cylinder-type models. But in the case of sodium, we have a higher range of orientation, so we start seeing things that are kind of similar to Bragg peaks. Or in the case of lithium, we actually saw from the cryo, we have much more chiral-like structures. But what we were really interested in is what was happening when we added potassium chloride. Because when we looked at the cryo-EM data and we resolved it down to the atomic level, we saw that the sample was not forming just a nanotube, because that's what we were hoping to see, but it formed these square-like nanotubes with 18 different conformations of the dipeptides in the asymmetric unit. And this is something that we couldn't have predicted, and we didn't expect at all. And most importantly, after a lot of studying and understanding the sample, we found that they only form if we shear the material overnight. So if we form the material on the bench by addition of the salts, we just get fibers, very, very thin fibers. So they need to be sheared. How do we understand what is happening? Of course, we turn to Rheo-SAXS. So this was done at diamond light source at the I-22 beamline. And what we did, we used a concentric cylinder cell to avoid that the sample would slip under the parallel plate because it's really, really viscous at the start. And then we monitor the sample at a constant viscosity, at a constant shear rate. And then we increase the shear rate over time to try to gain information and also get the formation of the nanotubes. Very interestingly, we see immediately from the viscosity data that the sample is really highly viscous, but drops in viscosity quite immediately as soon as we start shearing it. From the CoSAXS data, we start seeing the formation of cylindrical fibers, but these are quite small compared to the nanotubes. Interestingly enough, we don't see any changes until 128 minutes. However, if you look at the viscosity, there's quite a significant change throughout the system. So what seems to happen is that these two morphology coexist within the sample, but the formation of the second morphology is not correlated to the shear. And what we saw, if we then kept measuring the sample, is that over time, the hollow nanotubes will form. But on the level of the rheology, we see no changes. Up to 200 minutes, where you see the viscosity still the same as it was at 75 minutes, the sample then forms finally the nanotubes. So it seems that the transition is related to the application of the shear forces, not necessarily to just a shear thinning event, which is what we were thinking initially. And if we fit the data to a combined model, we can also track the appearance of the nanotube around 70 minutes in, and over time, the scale, so the presence of this nanotube, overtaking the cylinder and being more present at the end of the run. And again, we wouldn't have expected this to happen. So this is why Rheo-SAXS can be really interesting. Based on our observation, what we start to think it's happening is that when we add the salts at the start, the sample forms these very small fibers. And these small fibers are agglomerated and they stuck together because the salts is screening the charges on the peptides. And so they want to self-assemble. But if we shear them, we start to disentangle them. And these primary fibers then over time start to reassemble, self-assemble, associate laterally, and form these hollow nanotubes. This is also driven by the fact that the radius of these very small cylinders is the same as the thickness of the nanotubes. So we think that the initial protofiber is the same between the two samples. And this again would not have been possible to understand if we didn't do any Rheo-SAXS on the system. But clearly, it seems that there's quite a big gap in length scales. If you look at rheology, and then if you look at the nanoscale, we have quite a big gap to fill. And one way to fill this gap is to introduce a mesoscale level imaging. The way that we did this was done in collaboration with Chalmers University of Technology, with a group of Professor Roland Kadar, who have found a way to put all of this together at the CoSAXS Beamline and the 4MAX Beamline and MAX 4 to be able to do rheology, SAXS, but also polarized light imaging. If we combine polarized light imaging with rheology, we are able to understand orientation on the mesoscale level of the systems. And the way that this is visualized is by the appearance of this Maltese cross pattern. So what happens here, we have the system being irradiated with a polarized light. It goes through an analyzer at 90 degrees. And so as the sample is being oriented and it's aligned on the direction of the flow, the refractive indices of the optical indicatrix will be parallel to the polarization direction in 4 places. And because of that, we have the 4 fringes. In this way, we can then link mesoscale level orientation as well as nanoscale level orientation. The way that it looks like, it's a bit like this. So this is from experiments that we have done at the CoSAXS Beamline. So you can see this big gray machine is a rheometer. We have these 2 glass plates where the sample is sandwiched inside. We have a polarizing filter, 2 big lights coming from the top, and then we have an analyzer at the bottom with a camera looking down. And here you see the snout where the X-rays come out, and here is the window of our vacuum vessel where we collect the SAXS data. So how does this data look like? On the one hand, on the SAXS, we have our scattering patterns. So again, this is just the 2D data that we get from the sample. To analyze the orientation, what we do is that we take a slice of an azimuthal integration and we put it against time, or in this case, shear rate. So depending on the system that you're studying. And of course, the appearance of a preferential orientation will tell us that there's nanoscale orientation. We can then integrate this into azimuthal integration graphs, and we can then fit it. So if we fit the scattering intensity by the Hermann's orientation parameter, we can get information on the orientation of the sample, whether it's horizontal, vertical, or random. In the case of the PLI, it's a bit more difficult. So this is the image, the raw image that we get from the camera placed below the rheometer. And you see the appearance of the fringes. So this is the Maltese cross. We then take a radial arc, which is typically taken at the nominal shear rate, so 2/3 of the radius. And then we plot it against the shear rate or the time, again, depending on what you're looking for. And then this is also integrated, and we apply a similar level of analysis to this system to also understand the orientation on the PLI or on the mesoscale level. So this is how the data kind of looks like. So we have at the top here the viscosity. So this is just viscosity measurements, as I've shown before. Then the 2 time space diagrams of the PLI and the SAXS. What is important to note is that in terms of the PLI, what we quantify is really just the onset of the Maltese cross. We don't get any more information than that. So if it's higher than 0, we have a Maltese cross. In the SAXS, instead, as I've mentioned, you can quantify whether it's vertical, random, or horizontal. So this is an example from the group in Chalmers where they use cellulose nanocrystals. And as you can see, there's 3 different ones. So the B cellulose nanocrystals are formed mainly by bundles of the nanocrystals. The P cellulose nanocrystals are much more just crystallized, so a lot more just the cellulose nanocrystals by themselves. And the second one in the middle is a surface modified version of this last one, which disrupts the self-assembly, so it forms much more viscous materials. What was really interesting out of this data is that when we were thinking that maybe the mesoscale orientation and the SAXS orientation would happen at the same time, for most of these samples, this is not the case. For the CNCs that form the mandals, the PLI orientation starts earlier than the SAXS orientation. This is also the case for the surface modified one. But in the case of the much more less agglomerated CNCs, we see a much more simultaneous start of orientation. So this is suggesting to us that in these sort of biphasic suspensions, when we start to orient the system, we firstly orient the mesoscale level agglomerates, and then over time, there is a reassembly of the systems to orient themselves on the nanoscale level. If we look at much more concentrated systems, we have a very different cases. We can start seeing many more things, especially if they form liquid crystal faces. So we have a lot of color already at the start, but also we have a very good initial alignment, and that's typically due to the squeeze flow of the sample being put inside the rheometer. And then we have a progression of loss in this orientation over time. And this is possibly also because there is a sort of transition between the gap to then restructuring in the azimuthal level flow. And all of this can be analyzed using Rheo-PLI-SAXS, and we can get a lot of information with this. And we can also, with these sort of liquid crystal systems, look at the way that they form striatures of the sample. So here is the sample as it's being squeezed. So you see this different direction. And then as the sample is being sheared, we see the formation of these striatures that go along the direction of the shear. So when I found out about the Rheo-PLI-SAXS, I really wanted to be able to perform it on my samples, and this is how this collaboration started. And so we used the rheometer as a way not only to induce flow, but also to track information on the samples. So what we were doing, we used this gelator, LD2NAPFF, and we created a system that underwent a gel to salt to gel transition. So at the start, it's a gel, it's a solid-like material, it goes into a solution phase, and then it forms a gel again. This is done in a pre-programmable way because we include two different pH triggers within the system at the start. So at the start, the pH will slowly increase, form a solution phase as we're able to make our sample a bit more soluble, and then there will be a very slow pH decrease to form a gel again. What's really important about the system is that this process is heavily controlled by the concentration of your pH triggers, which means that you can very well control on a time level what is happening on the sample. So we knew exactly how long the solution phases last for. And because of this, we wanted to take advantage of this to create ordered materials. The way that we did this is that LD2NAPFF formed these very nice nanotubes that are very long, quite rigid, and they can be aligned really well using a rheometer. So we can see a Maltese cross pattern. And so we optimized the system to find a way to have a gel that collapses into a solution. We then shear it to align it, and then we allow it to regel again to form aligned gels. And this we have full control, but also the rheometer in this case is used to not only shear the sample, but track the formation of the viscoelastic gel, its collapse into solution, and its reformation into a gel. So we can track everything all together by just putting it in the rheometer and the rheometer program. And this is just a picture of the gel being put on the rheometer and me making sure that the gel was not getting broken. So the data looks a bit like this. And I'm going to start talking to you about what you cannot see, which is the rheology data. So on the rheological level, what we were able to see is that the system, when it was not sheared compared to when it was aligned with the shear, showed the same kinetics of gel to salt to gel formation, which means that our shear alignment was not affecting the sample at all during its evolution. But the final viscoelastic properties are different. So for the shear aligned systems, we have less stiff gels, so slightly more liquid-like, if you will, but they are stronger. So they seem to be able to persist a bit more shearing, which may mean that we have pre-encoded this response to shear by aligning them. If we look at the mesoscale, the data that you see at the top is the pictures from the camera. The sample that was not sheared looks just like an opaque gel, transiting to a final gel, and thankfully, the PLI analysis shows that there's no presence of a Maltese cross. However, in our shear-aligned sample, we see an immediate formation of a Maltese cross when we start shearing the material. And we shear the materials for, say, 70, 80 minutes. And when we turn off the shear, we see that the anisotropy is being kept, which suggests to us that on a mesoscale level, our sample is oriented. So we have oriented gels. And this we know because the rheology is telling us that we have gels. Interestingly enough, on the SAXS level, things look a bit different. When we looked at the SAXS, we saw the formation of anisotropy under shear, so the sample was getting oriented as we were shearing it. But as soon as we turn off the shear, we lose this anisotropy. The reason why that is, we think, is that we have these very small nanotubes. They have to form random crosslinks and networks to entrap the solvent and form a gel-like material. So it has to disrupt this alignment on a smaller length scale. But if we actually look at a mesoscale level, this event is still happening with a level of ordering. And this we wouldn't have found if we didn't do Rheo-PLI-SAXS. If we look then at the SAXS of the data, both of the samples fit to nanotubes and with radius of around 18 nanometers. And what we were able to see is that our sample that wasn't shear aligned looked the same throughout the whole process. But we have a very small reduction of radius of around 1 nanometer in the shear aligned material. What we think is happening here is that maybe we're allowing the molecules to pack a bit better because we are reducing the presence of bubbles in the sample. As you can see from the data here, there's production of CO2. So in the initial gel, we're trapping them in. But if we shear align the sample, we also don't have those bubbles in. So we might actually have a bit more space for the molecules to pack better together into their nanotubes. Of course, we're not just limited to Rheo-PLI-SAXS in room temperature. We also have ways to do it at high temperature. So this was done quite recently. We have Rheo-PLI-SAXS, but also we were heating the sample up to, I think, 240 degrees. But we can also do temperature-controlled and moisture-controlled SAXS wax and dynamic mechanical analysis by using these particular cells. And this is really important because these are sample environments that are very useful for industry or also for people who work, say, for example, in food, because this can really mimic the processing of a material as it's being studied or as it's being processed. And so we can really try to study the material as it will be made on an industrial level. Of course, we always like to finish these talks about Rheo-SAXS by showing you things that people do not want to see. Roland has always mentioned to me that once you start putting things in a microscope, you start finding things that you maybe do not want to know. And this is what happens typically in SAXS. So now that we can look at the sample, we can see the formation of bubbles. We can see, for example, samples running away from under the geometry or sample being completely blasted with X-rays. And of course, this is visible now because you have a camera. But if you do a normal Rheo-SAXS experiment, you might not see it. And sometimes you will get very good X-ray data and you think, oh, wow, my sample is growing. You might just be blasting it through with X-rays. And if you're really interested in doing these sort of very cool Rheo-SAXS experiments, there's two beamlines here at Max 4 that do it. So CoSAXS and 4Max. Max 4 is a world-first fourth-generation source. We have ultra-low emittance, and we have really high brilliance and coherence. So we can really study structure, dynamics, and functional studies for soft matter, life science, and materials. And because of it, it's really ideal for in situ, operando, and time-resolved experiments. And because of the rheology, we have a science initiative at Max 4, so it's ARTSI, Advanced Rheology and Tribology Science Initiative, which brings more than these people that you see here together, and we keep growing our team. But basically, the idea is to develop unique Rheo-SAXS experiments, tailor them to user support, and also tailor them for the specific requirements that you might want to do at Max 4. So in summary, what is really cool about hierarchical functional materials is that their macroscopic behavior is really well linked with their mesoscale and nanoscale. And so in situ, multimodal characterization is really important to understand structure property relationships. In this way, we can combine rheology and SAXS wax to obtain this sort of interactions with them, to study shear-induced phenomena or also monitor mechanical changes. If we then start introducing complementary probes like polarized light imaging, we can further bridge this length scale gap and get orientation information on two length scales while also inducing flow orientation. We can also achieve controlled temperature and humidity, which means that we can expand our experimental condition to study materials in operando or under processing conditions. And that's all for me. Of course, I would like to thank Dave for all the help that he gave me during my PhD. So a lot of this work was part of my PhD, but also then my collaborators here, Roland and Marco from Chalmers University of Technology, the rest of my team at CoSAXS for all the help, and you for your kind attention. And I would like to finish this presentation to show you that outside of the lab, I still do rheology, but I just use it with my legs. And yeah, thank you so much. And if you have any questions, I will be happy to take them.
Thank you very much, Simona, for this very interesting talk. So please, if you have questions for Simona, just go ahead.
I have one question.
Yes.
So thank you for this very interesting talk. If I didn't know that you had like just a few days to prepare it, I would have never guessed. Um, so my question is when I hear like phase change like that, like I'm not used to work with liquid or gel, whatever,
hmm
but there's probably like but there's a index refraction change. Like how does it impact your SAXS signal?
Um, I'm not really sure. We have not seen much of a difference, but I think it's because my samples, so some of them change in terms of like absorption mainly, but in
Mm-hmm.
terms of my samples, we've not seen much of a change. Most of them are not also quite turbid, and so they tend to be quite similar. But
Okay.
I'm not really sure about other systems.
It's probably negligible.
It's probably negligible for
Okay.
most, and
Mm-hmm.
I think it's more so it becomes more of a fact of the understanding what type of imaging you have to do.
Okay.
But we have seen not much of a change in that case. But yeah,
Okay. Thank you.
thank you.
Okay, other questions, please?
Yeah.
Jakub, I think.
Can you also control the temperature? And if yes, what's the range?
So depending on the type of system that we use, we can control the temperature in all cases. So I'll show you here. So we have I'm coming. Okay. Yes. A lot of very nice things. Um, okay, yes. So we have this temperature hood that you see here. So this is like the one that comes with the Anton pyriometers. I think we can go to 250. But of course, like then we have all of these other machined bits to be able to keep the heat, of course. And also we have to be careful because our windows cannot really take that much temperature. But we're trying to buy more temperature resistant windows. And then we also have this humidity cell and temperature control cell. I'm not sure what the temperature it goes up to. I'm assuming it can go quite high, but I will have to look into that or talk with the guys at Chalmers. But we have quite a good temperature range.
Great, thank you.
Thank
Okay,
you.
other questions? I have one actually. I don't know if I understood correctly. Somewhere in your presentation, you said that you obtain nanotubes due to shear.
Yes.
Only nanotubes?
No, you can anything that is long-ish or prolate particles will likely orient under shear. Just I personally have used nanotubes or nanofibers. That's typically what most of my samples form. And in this particular case, we saw that these square nanotubes formed only under shear. But anything that can be sort of elongated, then you would imagine that instead of being like random motion, you can orient it by applying the shear on them. And we're doing a lot of studies now with prolate particles in turbulent flows.
Okay, thank you. Other questions?
Yes.
Yeah, please.
So if I remember correctly, at the beginning of the presentation, I think you said that SAXS measurements were easy measurements. Am I correct?
Maybe I must have said easy, but nice.
Okay, maybe I misunderstood because it seems like quite complex. And now I understand better why some users might be afraid to do SAXS.
So simple SAXS is quite easy because you just put the samples
Okay.
as they are. Typically, if it's liquids, you just fill capillaries, or we also have a liquid handling robot, so you just fill a plate of them,
Oh,
put
nice.
the names on, and let it run. And the only thing you need to care about is radiation damage, or say that you have thick samples, then maybe you need to use thinner samples and a bit of consideration on contrast. So normal SAXS, I think it's quite, I wouldn't say
Oh, okay.
easy, but it's quite straightforward.
Yeah, okay.
The analysis, I think it's harder
Yeah,
in those cases. The Rheo-SAXS experiments, yes, they are tough. You really want to have somebody who knows about rheology at the same time as SAXS,
Yeah.
because of course, like we also have these massive air gaps, so maybe your sample will not scatter that well. It will be mainly just water. You have multiple scattering in your materials because there's a lot of path that the
Yeah.
X-rays have to go through. So there's a lot of considerations there. So you have to really discuss it, which is why we have the science initiative, Max 4. And so we typically get people to talk to us, and then we design the system with them. And typically, if they come to the Rheo-SAXS, we will be there to set up the rheometer and the SAXS for them. So then what the users have to do, make a rheology program, put the sample in, measure the SAXS, and we deal with the harder bits. But it's mainly more so of a just synchronization, hoisting a 20 kilogram thing inside the beamline and aligning it and fitting it in the very tiny space to have minimal air scattering.
Yeah.
Yeah.
Perfect.
Thank you.
Okay. If there are no other questions, thank you very much, Simona, for
Thank you.
this nice talk. And looking all of you, I'm waiting all of you to the next webinar. So have a good day.
Thank you.
Thank you.
Bye.
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 Bye.